Here's another really cool idea. It's going to be talking about cell potentials in actual cells. And so my picture of a cell here is going to be a chemist's version of a cell. But let's suppose that this is the cell membrane of a cell, and that here we have inside a cell, and here we have outside a cell. Now, a typical concentration for, let's say, calcium inside a human cell would be 1 times 10 to the minus 4th millimolar. So 1,000th of a molar. And so inside a cell we have the concentration. Outside a cell, which could also be called inside the blood, we might have a concentration of 3 millimolar. And the question is, based on this difference in concentration, what is the cell potential? And because these cell potentials are what eventually we can talk about leading to the firing of neurons, because neurons are electrochemical devices that fire and create signals in the brain. And we're not quite there yet, but this is the idea. And we're going to have to develop a new concept, which is that the Nernst equation can be used or applied to half reactions. And the idea is that somewhere around here there's also the other half reaction that we need. But let's talk about the reduction of calcium ion as our half reaction. That's going to take calcium 2 plus 2 electrons, goes to calcium solid. And we're now going to apply this. So inside the cell, we're going to use the Nernst equation, and it's going to look like this. So E naught inside, sorry, on the left hand side there's no naught there, equals E naught inside minus RT over NF ln Q. And plugging in our terms, well, our standard cell potential is just going to be for calcium, which is not on our typical list, but it is minus 2.76 volts. And then here we're going to have RT over 2 electrons for the F. And our concentration here inside the cell, since it's on the reactant side, is going to be 1 over, well, 1 times 10 to the minus 4th millimolar equals 1 times 10 to the minus 7th molar. Though they tend to report them in millimolar when they're talking about cells. But the number we need is 1 times 10 to the minus 7th there. And that will be our cell potential inside the cell. Outside the cell, we can write the same equation. And now it's 3 millimolar, which is 3 times 10 to the minus 3 molarity. Oh, that's from my last slide. Like so. And now what we can do is look at the concentration, or sorry, the cell potential difference from outside to inside the cell. So delta E equals E out minus E in. That's going to equal these two terms here are going to be the minus 2.76 volts. So those two terms cancel. And we're left with this part minus this. Where we get two positives there, and really you're going to take, and any time two things are negative, let's say this, are added together or subtracted in this case. So the subtraction is going to move this up to the top. Well, let's just go ahead and do the numbers here. We've got enough. So, well, let's do one more step. Minus RT over NF. Positive. Plus. Oh, we've got our RT over NF outside. And so now we have to do the two natural logarithms and then multiply it times RT over 2F. So natural logarithm of 1 over 1 times 10 to the minus 7. So 1 exponent 7 minus 1 over natural logarithm is 16.1112. Here, 3 exponent 3 minus 1 over natural logarithm minus 5.81. Do this subtraction. I get 10.3. I then multiply it times all these factors, 8.314 times 298 divided by 2 divided by 96,485. I get 0.132 volts. Not a large number, but not a small number either, and they're typically reported as millivolts. There is a 132 millivolt difference, at least in this approximation, created just by the calcium ions and the concentration difference across the cell membrane. And if you add up all of the different cell potentials across a membrane, you can get up in the volt range, which is approximately what you need to fire a neuron. Pretty cool.